Hi folks, so today I wanted to do a numerical example of how to handle negative externalities in this market-based supply and demand framework that we've been talking about. So specifically, a negative externality is one example of a way in which we can get an incomplete market. And an incomplete market would lead to a market failure, i.e. a way in which even though supply and demand come to equilibrium, that equilibrium allocation for price and quantity will not be socially efficient because of this negative externality. So let's see how that plays out on this mathematically in this market-based framework. So I'm gonna start my screen share. In just a second. Great. So what I'm gonna do is I will draw an axis down the side here. So I'll just use the full axis this direction. And I'll go over 6, 8, 10 or so this direction. Okay. And this here is going to be our Q, or our quantity of the good that is supplied to the market. And this here will be in units of dollars per unit quantity on that end there. Now, somewhat arbitrarily, I'm just going to pick some functions here. And so we are, just as a reminder, maybe I'll put a little heading up here that tells us that we are dealing with an incomplete market. In other words, one example of a market failure, and we are specifically handling the negative externality case. And this is a case like if you had someone producing a good that required the emission of pollution per unit good. That pollution would not normally be incorporated into the decision-making of the producer and is thus a negative externality because the cost of that pollution ends up being borne by someone other than the producer making decisions about pricing and production. So what we're going to say is, because we're only handling the negative externality, we're going to assume that the demand function is equal to the marginal benefit for society. So we're going to say the demand is equal to marginal benefit, and I'm just going to say, let's just say that it is 9 minus Q. So I'll do 9 minus Q. So I'll go ahead and mark that up here. So I'll say, all right, well, this is 0 down here, and I'll count off to 10, 6, 8, 10, and then I'll go up this way, 2, 4, 6, 8, 10. Here's 9 here. And so this demand function is going to intersect this axis at 9. And then it's just going to have a slope of -1. So it's going to have a rise over run of -1. For every time we move over in quantity, we go down exactly 1 in the price that they are willing to pay, that these consumers are willing to pay. So I could just draw that. I could draw little dots here and then trace those out. Or since I've got this fancy tool, I know that this line will end up crossing through those and will end up landing at this point right here. So that should give me a pretty straight line that represents the demand function there. So that's what we've just, this is a reminder, this here is the demand function. And then now we're gonna go and let's say I told you that the supply is only, in this case, equal to the private marginal cost. So this is the marginal cost just to the producer. So the producer's marginal cost or the private marginal cost. And I'm gonna just say that that's equal to 0.6 Q. So for every unit of production, then there's a cost of 0.6. So so that sort of tells me that if I were to produce 10 units of this, then I would have a cost of 6. So, you know, if you think of this 0.6, you can remember this is like 6 out of 10. So it's like rise 6 for running 10. So I'm going to run over 10, and then I'm going to rise up 6, and I'll land here. So that's where I'm going to draw this line. So I'll go back and do that. So draw this from 0 to, and I'll just better put a point there so I don't accidentally mess this up, as I'm known to do. All right, so then the last thing, because this is a negative externality, kind of hinted that the supply function isn't capturing all of the costs. So where are the other costs? Well, the society pays the rest of those costs. And so the societal's costs is our marginal damage function. So I'll choose a different color, I'll say orange, and this will be, the orange is not very dark here. Why don't I choose a different color like green, and I'll say the marginal damage, I'll say is 0.4 Q. So what this is saying is that for every unit of the good that is produced, the producer pays a cost of 0.6, whereas society pays a cost of 0.4. So whereas the supply function, which I guess I could have written here, supply equals PMC, this marginal damage function, for every, so this here, I guess I could again write this as 4 over 10. So this is saying that for every 10 units provided, then we rise up 4, and this is where the marginal damage would end up crossing. So I am going to just draw that there. All right, and so that is our marginal damage function. Now, just looking at that, we know that this market will come to equilibrium where supply is equal to demand. And so I could go into here, and I already know exactly where this market's going to come to equilibrium. It's going to come to equilibrium right here. And so I can now solve for where this market comes to equilibrium, the market equilibrium. And so that will be the combination of these two. Maybe I'll use a different color for that. Combination of these two. And if, so to find the QM, PM, which is the allocation at the market equilibrium, I'm just going to set supply equal to demand. And so I'll set 9 minus QM equal to 0.6 QM, which with a little bit of algebra, I can move the QM to the other side. So then I get that 9 is equal to 1.6 QM. So all I did was I added QM to both sides. I got rid of the QM on the left-hand side and then added it to the right-hand side. That's why I went from 0.6 to 1.6. And then I can solve for that QM just by dividing 9 by 1.6. So I can say the QM is equal to 9 divided by 1.6, which if I get out a calculator, as I'll do here behind the scenes, 9 divided by 1.6 is 5.625. So that looks about right. You know, so this is, if I were to drop this down, there it is right there. That is my QM. And then I need, well, what's my PM? What's the price at the market equilibrium? Well, all I can do is just plug that QM back into either the supply function or the demand function. And that should give me the price that corresponds to that. They'll both give me the same answer. So just because it's easier, I'm going to just plug it into the supply function. And so I'll say, well, that's 0.6 times 5.625. And that tells me that my market price is, and I'm going to use a calculator here, so 0.6 times 5.625, 3.375. And that looks about right here. So if I were to draw this over, then I give my market price around 3.375. Okay, so that's where the market will hit. But we know that this is not going to be the socially efficient equilibrium because this quantity and price did not take into account the marginal damage that society is paying. So what we can say is, well, what if we were at the socially efficient equilibrium? Or put another way, how much damage are we really doing in terms of our net benefit, our marginal benefit minus our true cost? And so in order to figure that out, we need to solve for the, and I guess I'll use maybe a different color here, maybe this light blue color, our societal marginal cost is going to be equal to our, maybe I'll move this up a little bit to give me a little room. Okay, so our societal marginal cost is going to be equal to the private marginal cost from the producer plus the marginal damage. And if I just plug those things in, that's a 0.6 Q plus a 0.4 Q. And if I combine those things, I just get a 1.0 Q, or just Q. So I can then plot that. So the societal marginal damage is just going to be a line of slope 1. Rise over 1 is equal to 1. So if I were to run 10, I would also rise all the way up to 10 here. And so I'd be up here at this point here, because that's in the middle of this text. Then I'll just say, well, if I were to go over 8, I would come up 8. And so I'm just going to end it right here. So I'll put a little point there, this point right here, and I'll connect those dots. And if I didn't have this handy dandy tool, then I would just, on the grid, I could just move up, 1, 1, 1, 1, and I would make points along each one of these and then connect those dots. And so that ends up being my societal marginal cost curve, and where the societal marginal cost curve intersects the marginal benefits curve, which is this demand curve, so as a reminder, then that ends up being my actual efficient equilibrium. That's where we kind of want to be. That's where the benefits to society are maximized. Now, the gross benefits to society, you get more of them at the other equilibrium. But the problem is there's a cost that is imparted that when you include the additional costs, then you end up, the net benefit ends up being less at the other equilibrium. So let's try to get a better understanding of how that works here. So what I'm going to do is I'm going to take that point, that QM point, and I'm going to extend it up to right here along the societal marginal cost. And then I can ask, what is the societal marginal cost at the market equilibrium of this 5.625? And so what I find there is that this point, I can say, well, I know that the SMC is equal to just Q. So at QM, which is 5.625, then I know that the societal marginal cost is just going to be equal to the same thing, 5.625. Because if I plug in QM 5.625 into the societal marginal cost, which over here is just Q, I just happen to get the same number. So maybe that was a poor choice on my part to illustrate this. I hope that's not confusing, but I just plugged in, this here is again just QM, and this here is the SMC function evaluated at QM, and they just happen to be the same. And so here, now I know that my societal marginal cost is clearly larger than my marginal benefit. Because remember that the marginal benefit that I'm getting is way down here equal to PM. So the marginal benefit that so I guess I could write that down here. Down here, this is 5.625 is the quantity, and the price, which corresponds to the marginal benefit that I'm experiencing at this quantity, is only 3.375. And so this here is the marginal benefit at QM. So this is telling me that my marginal cost at the market equilibrium is actually larger than my marginal benefit. So this tells me that my net benefit, my gross benefit minus cost, would actually be increased if I consumed less. Because even though consuming less gives me less benefit, it also gives me less cost. And the benefit, the decrease in cost is going to actually be larger than the decrease in benefit. And so I actually do better. And so it is a Calder-Hicks improvement if I shift this way up towards these things, and they balance out again up here. And so this point, I'd like to know what's going on at this point here, exactly what are the coordinates of that point. And so I can then set the SMC, maybe I'll go and I'll use a slightly different color here, I don't know, gray, and I'll set this SMC equal to marginal benefit. And so that would be Q is equal to the marginal benefit, which I've written down here as 9 minus Q, which I can then bring the Q over to the other side. So that tells me that 2Q is equal to 9. And so Q, and I guess I should make these all Q star because it's the efficient Q. So then Q star is equal to 9 divided by 2, or 4.5. So, and then I want to know, well, what is the P star? So what is the price at that equilibrium, at that socially efficient equilibrium? And in which case I can just plug in Q star into the marginal benefit curve. So I know that 9 minus Q star is just equal to 9 minus 4.5, which is equal to 4.5, which happens to then that's equal to P star. So P star is equal to 4.5 and Q star is equal to 4.5. So this point right here is, which maybe I'll write it in blue just to make it kind of match the point. This point here is 4.5 comma 4.5. And where this 4.5 is Q star and this 4.5 is P star. And so I can then drop this down. There's my Q star, and I can drop this over, and there is my P star. Okay, so we're almost done. We've solved for all of the points we need. And well, actually, we will end up needing one more point that we can solve for. And that ends up being this point right down here, which is what is the producer's marginal cost at the socially efficient equilibrium. So what would the producer pay to be producing these things if we force the producer to produce less? Do we force the producer to produce the Q star? And we can do that just by plugging in Q star into the PMC. And so the PMC at Q star is just equal to 0.6 times Q star, which is 4.5. And if I then do the math there, 0.6 times 4.5 gives me 2.7. And so that tells me that this point right here occurs at 2.7. And so I guess I could write this as Q star, comma 2.7. Okay. So now what we can do is we can calculate the producer surplus and consumer surplus at the efficient equilibrium. We can then see how much producer surplus and consumer surplus is lost by operating at the socially efficient equilibrium. And then we can calculate the marginal damage. And if we find the marginal damage is greater than the producer surplus and consumer surplus lost by operating at the socially efficient equilibrium, then that tells us it's actually better to operate at the socially efficient equilibrium as we're expecting. So let's first calculate up here. This region, this triangular region up here, that region is the producer surplus, is the consumer surplus at the socially efficient equilibrium, Q star. Just kind of shading this. And so in order to calculate that consumer surplus, that's just going to be equal 1/2 times base times height. And so for this triangle, I know that the base is just this length here, which if I go down, I find out that's Q star. Q star I know is 4.5, so that's 1/2 times 4.5. And then you can say, well, then what is the height? Well, the height is this here, and that's just 9 minus whatever P star is. P star we've already solved for is 4.5, so that's also 4.5. And so 1/2 times 4.5 times 4.5 is 10.125. So then we need to figure out the consumer or the producer surplus. That's a little more exciting because it's a different shape. So it is the shape that's this trapezoid down here. So I'm going to go along the producer's cost up until this point, and then go up and then go over. And so this region here that I'm highlighting, that region is the producer surplus at Q star. And again, I'll shade this. Maybe I should shade a different direction, maybe this direction. All right, and it stops short, right here. It isn't the full triangle because the producer is not producing where supply is equal to demand. The producer is stopping a little bit early right here. And so the producer, if the producer is not thinking about the marginal damage, then the producer is going to feel like they actually could produce more, and they could produce more at a slightly lower price. And so it's almost like the producers, the market itself, if you didn't consider the marginal damage, the market itself would equilibrate over here where supply is equal to demand. Producers, as they're being competitive, will lower their prices. As they lower their prices, they'll entice consumers to buy more, and the amount of quantity supplied will move over to the market equilibrium. But if we had a way to hold them, say with a tax, if we had a way to hold them over at this Q star, then they're going to stop kind of early, and this is the producer surplus you get. And so we can calculate the producer surplus at this Q star, and you can either calculate this as a rectangle and a triangle. So you could go and say, oh, I see this rectangle up here, and you could figure out the length of this rectangle, this leg of the rectangle, and then the length of this edge of the rectangle. And then you could also calculate the area of this triangle here. So you could figure out the height of this triangle and the width of this triangle. And you've got those things together, and then you add this area to this area, and then that would end up giving you the producer surplus. What I'm going to do here is a little trick where I'm going to use a special formula that we use for trapezoids, which is 1/2 times the base times the sum of the two different heights. And I'll show you what I mean by that. So I can say the producer surplus at the socially efficient equilibrium, is equal to 1/2 times the base of the trapezoid times one height plus the other height. And what I mean by base here is going to end up actually being this part of the trapezoid. And maybe it's easier for me to, instead of saying base height 1 times height 2, that's just kind of how I remember it in my head. Why don't I change that to height times base 1 plus base 2, in which case this I'm viewing as the height, and this I'm viewing as base 1, and this I'm viewing as base 2. So if I do that, then, and I'm going to just do a little erasing here of this demand equals NB. Maybe I'll rewrite that below it, just to give myself some room. And that is going to be equal to 1/2 times the height here is just equal to Q star. Q star is equal to 0.5 or 4.5. And then these two bases, I have to calculate what's this length here. Well, that's just going to be equal to 4.5 minus 2.7. So I could put that in there. 4.5 minus 2.7. And then the other base is just this full length here, which is just P star, which we happen to know is equal to 4.5. So that's fortunate. And so if I were to then, type that into a calculator, then I have 1/2 times 4.5 times this 4.5 minus 2.7 plus 4.5, and that gives me 14.175. And so that is my producer surplus. So maybe I'll just write those in. So the consumer surplus, I'm just going to erase a little portion here, and I'll say that's equal to whatever I found, 10.125. And the producer surplus, I'll erase a little portion here, and I'll say that is equal to 14.175. All right. So you might. So then we're interested in two more areas: the area of this triangle, which is the amount of producer and consumer surplus lost by operating at the efficient equilibrium, and the area of this triangle up here, which is the deadweight loss, which is the loss to society by operating at the market equilibrium instead. So this triangle down here, this is the lost producer surplus. I'll say the lost consumer and producer surplus at Q star is just equal to 1/2 times the height times the width of this triangle. Now the height of this triangle is just the difference between Q star and QM. So that's Q star minus QM. And then the other dimension of the triangle is just the difference between P star and 2.7. So if you don't see that, this first thing here is just this distance. So we'll call that the height. And then this here is just this distance here. We can call that the width. And I know that P star, that's equal to 4.5. So I know enough to calculate this triangle. And I see that, and then the Q star I can put in here, I think that's also 4.5. Q star is equal to 4.5. QM, we solved for a while back. QM is equal to 5.625. And of course I meant to flip those. So, so this here, if I were to write this, imagine that these were flipped. So I'm just going to flip the order of those. So this is supposed to be QM minus Q star, or Q, the higher one, QM minus Q star. And so that is 5.625. And this here is 4.5. So if I type all of that into a calculator, so that I have 0.5 times 5.625 minus 4.5 times 4.5 minus 2.7, and I hit enter, then I find out that is 1.0125. And so I can maybe highlight this area here, that area is equal to that, 1.0125. And so the last area that we need to calculate is this deadweight loss area, which is up here. And we do similar sorts of triangle math. So we can say then that the deadweight loss I can say deadweight loss at the market equilibrium is equal to 1/2 times, fortunately, it is the same width as before. So that's the QM minus Q star, but it is a different height. So now I'm working with this height here. And we know that this height is 5.625. That's the social marginal cost. And then we know that down here, that is 3.3725. That's the marginal benefit there. So I can put those things in, 5.625 minus 3.375. And then that deadweight loss, if I calculate all that out, I've got 0.5 times the quantity, 5.625 minus 4.5 as before, times 5.625 minus 3.375, and that's equal to 1 point, and I'm just going to round here, that's equal to 1.266. And so that there is the deadweight loss. And as expected, the deadweight loss, 1.266, is larger than what we lose in producer and consumer surplus by operating at a socially efficient equilibrium. So even though moving from this point QM down to this point here looks like we're actually losing out on net benefit, what's not only are we losing that, we're actually then getting rid of the cost that is being paid in terms of the marginal damage. And so this here is the accumulated effect of that additional marginal damage that the producer wasn't considering when they were making production decisions, and the consumer wasn't considering when they were making decisions about pricing and all of that. So, and so that's why this ends up being a Kaldor-Hicks improvement, why this ends up being the efficient equilibrium. To put that one more way, as I'm just going to put on a different page here, if you remember that back before we started drawing these marginal curves, marginal benefit, marginal cost curves, when we actually considered the total benefit and total cost, then what we would get is we would get plots that looked like this one. So if we view this in terms of quantity, and this in terms of dollars, not dollars per Q, but actually dollars, then what we find is that the marginal benefit, rises and tapers off, or not the marginal benefit, the total benefit. So the benefit, it rises and tapers off like that, and the producer's cost rises like that, so we can call that the cost, Q, and this is the cost just to the producer. And, but we know that there's an additional cost to society, which I maybe even put in dark green, and it rises maybe at a lower rate, but it still rises. And so you can think of this as, so if this is if the other one was the cost to the producer, then you can think of this new curve that I've drawn as the marginal damage cost, or the damage cost, not marginal anymore, just the cost due to, you know, additional damages. And so if we were to add those together, then we would get an even steeper rising cost curve. And so the total cost curve, which maybe I'll write in that. I'll do it in the light blue color to be consistent. So this is like even steeper rising. And so you can think of this as the true cost to society. Now, what we had said before is that you maximize the distance between these curves when their slopes are parallel to each other. And so there is a point that will maximize the distance between this red curve and this black curve. And you know, because I just kind of eyeballed these, then you know, if I figure this is kind of the slope here, and if I down here I get a slope that's kind of around parallel, and we would say, well, this point right here, that maybe maximizes the distance between those two curves. And so it may be here that this point is the market equilibrium because it maximizes the distance between these two curves. That's kind of the net benefit. Now, this steeper curve, that point where these things are maximally bowed out is going to happen at a lower quantity. And so that there's going to be some other point, let's say it's around here, that maximizes the distance between these two curves. And we can call that, you know, Q star. And so what we're saying is that when you consider all of the costs, if you were to move up to this point, then your net benefit would actually contract. So this would shrink. It's like, I'm just going to emphasize that this is a shrinking net benefit. So when you consider all of the costs, so this curve here, then you find out that the maximal distance between the total benefit and the total cost happens at an earlier quantity. But when you only consider the producer's cost, then it looks like you maximize the distance between this curve and the cost curve at a higher quantity. And so that's all that we're formalizing when we go to this marginal benefit and marginal cost curve, is that there's a different intersection point because there's a steeper climb in the marginal cost curve when you consider both the producer's costs and the marginal damages. All right, so that's basically a numerical example of how you can calculate all of these different triangle regions here. I leave for an exercise for you, if you would like, to actually go ahead and calculate the total benefit to society at this QM, at this market equilibrium. And you're going to have to be careful there because when you calculate the total benefit there, you're going to need to include not only the area of this triangle, but also the area of this cost. You're going to have to subtract that off. And what you'll find, as kind of expected here, is that the benefit under this scenario, where this is a negative here, this area here, is going to be less than the benefit under this scenario. And that's why that's a socially efficient equilibrium over here. All right, so that's our negative externality case. I hope that helped.